Okay, so finally, we're at the point where we can talk about what you've all been waiting for, the Series Hall of Fame. It's in your book. I believe the page number's right. You can check me on that. So the Series Hall of Fame, some of them you already know about. 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n. And of course, r, the radius of convergence, is 1. And the interval of convergence is just from -1 to 1, right? So that's what you already know about geometric series. Of course, that should be in the Hall of Fame, right? But then sine of x turns out to be this guy. Notice the exponents are odd, and the sine of x is an odd function. It's very important you can write these out longhand. Okay, yeah?
Can you make it a little bit bigger?
Yeah, sorry. Let me make it a little bit bigger. Let's go. We can't do it. 150, we can do it. Okay. It's very important you can write these out longhand. It will be very helpful to do that. So let's write a couple of these out longhand. Make sure you know how to do it. So what would this guy look like if you write it out longhand? So what would so it's the sum n equals 0 to infinity, -1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. So you would derive this the same way we did for cosine of x. Start taking derivatives, look for the pattern. What would you get? What would the first term be if you plugged in n equals 0? So if you plug in n equals 0, what do you get? X. And then it's going to alternate from there, right? Minus, what's the next one? If you plug in x, n equals 1, you get x to the, so you plug in 1 there, 2 times 1 plus 1, x cubed over 3 factorial plus, you plug in 2, you get 2 times n is 2 plus 1 is 5. X to the 5 over same thing factorial. Now you got the pattern. What's the next one going to be? Plus dot, dot, dot. Now, your teacher in trig told you that the sine is an odd function. Here's proof, right? What's an odd function? You take sine of negative x, you can pull the negative out front, right? Why can you do that? Because when you write it as an infinite polynomial, a polynomial of infinite degree, it's not really how we say it in most books, but we kind of think of it that way secretly. You plug in x for negative x, you can factor that negative out and get the same formula you started with, right? So sine of negative x is the opposite of the sine of x. That's why it's an odd function. And so compare that with what we got for the cosine of x earlier. Remember that was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Cosine's an even function, which again, your teacher in trig or pre-calc told you that as well. Okay? So this, whether or not you want to admit it, this is beautiful. We've turned these complicated transcendental functions, they're called, trig functions are called transcendental functions. We turned them into polynomials in a very real way. Not the kind of polynomials you messed with in pre-calculus, but really they act like polynomials. So what's another cool one? Look how, okay, when I say cool, I mean mathy cool, not real life cool. Look how easy e to the x is to remember when you write it out longhand. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on. And then you should be able to write it. It actually looks better in the summation notation. Oh yeah, the sum x to the n over n factorial. It couldn't get any easier to remember than that, right? There's a tangent inverse one that you could derive using the techniques I've shown you. And there's a natural log of 1 plus x one you could derive using the technique from the other day or using power series.